Welcome to our presentation on the design of a passive solar heating system using a Trombe Wall concept. Today, we are going to discuss how sustainable engineering solutions can help reduce energy consumption in buildings while also minimizing environmental impact. First, let me introduce our group and our team members. We are from Group 9 and the members are Nadija Tisun, Vishwa Kaushalya, Tosindan, I myself Varuni and Vasikaran. During this presentation, we will explain the problem we identified, the design requirements, the conceptual design and working principle, the engineering analysis and calculations, and finally, the expected outcomes, limitation, and future improvements. So, let's begin with the roadmap of our design process. First, we will discuss the problem and context, mainly focus on the energy crisis and environmental issues caused by conventional heating system. Next, we will explain the functional and non-functional requirements that guided our design. Then we move into the conceptual design section where we introduce the Trombe Wall passive heating concept and explain how it works. After that, we will present the engineering analysis, including the governing equations and thermal calculations used to evaluate system performance. Finally, we will conclude with the expected outcomes, evaluations, limitations, and future improvements of the system. Now, let's move to the problem identification. Today, buildings consume a significant portion of global energy, especially for indoor heating purposes. Most conventional heating systems depend heavily on electricity or fossil fuels. Because of this, buildings contribute greatly to high energy costs and increased carbon dioxide emissions. And another major issue is that many buildings have poor thermal insulation. Heat is rapidly lost through walls and windows, which increases the need for continuous HVAC operations. As a result, operational and maintenance costs become very high while environmental degradation also increases. To address these problems, our design objective was to create a zero running cost passive solar heating system. Next, we identified the functional requirements needed for an effective Trombe Wall system. First, the system must absorb solar radiation through a south-facing glass surface. This allows maximum solar energy collection during the daytime. Second, the wall should be able to store and release thermal energy with a delayed heat flux of at least 150 watts per square meter. The design also includes air vents to create natural convection airflow. Warm air rises into the room while cool air returns through the lower vent. Additionally, the system should support passive cooling mode to improve thermal comfort during warmer conditions. Finally, vent dampers are required to prevent reverse thermosiphon circulation at night, which would otherwise cause heat loss. Now, let's look at the conceptual design and working principle of the Trombe Wall system. During the daytime, sunlight passes through the glazed surface and heats the dark-colored thermal wall behind it. The air inside the gap becomes warm and rises upward due to natural convection. This warm air enters the room through the upper vent while cooler indoor air returns through the lower vent. This process creates a continuous thermosiphon airflow without using fans or electricity. And at the night time, the vent dampers close to stop air circulation and prevent heat loss. The heat stored in the masonry wall during the day slowly conducts inward and radiates into the room throughout the night. Because of this delayed heat transfer, the Trombe Wall acts as a natural radiant heater and helps maintain indoor comfort even after sunset. In this slide, we present the detailed design specification and major components of the system. The thermal mass wall is made of a 350 mm thick concrete wall which provides high heat storage capacity. For the glazing, we selected 4 mm clear tempered glass. This allows solar radiation to enter while protecting the system. A 50 mm air gap is maintained between the glazing and the wall. This spacing was optimized to improve natural convection airflow and heat transfer. High-density foam insulation is added around the frame edges to minimize unwanted heat losses. Each component plays an important role in improving the overall thermal efficiency and stability of the Trombe Wall system. To evaluate the performance of this system, we carried out engineering analysis using thermal equation. First, we calculated thermal diffusivity, which describes how quickly heat travels through the wall material. The equation depends on thermal conductivity, density, and specific heat capacity of the material. We also use the time lag formula to determine how long the wall takes to transfer absorbed heat from the outer surface to the indoor environment. In this equation, L presents wall thickness and P presents the 24-hour heating cycle period. These calculations are important because the success of the Trombe wall depends on delayed heat transfer during the nighttime hours. After performing the calculation, we verified the thermal performance of the systems. The results showed that the design wall achieved a time lag of approximately 8.722 hours. This means that the heat absorbed during the daytime is released during the colder nighttime period, which is ideal for indoor heating application. The calculated heat flux was around 198 watts per square meter, which satisfies the required performance criteria. Therefore, the mathematical analysis confirms that the proposed Trombe wall design can effectively provide passive heating with good thermal efficiency. The proposed system provides several important benefits. First, it improves thermal stability by reducing indoor temperature fluctuation. The wall absorbs excess daytime heat and releases it gradually during the night. And secondly, the system significantly improves energy efficiency. Our analysis estimates up to a 70% reduction in supplemental heating requirements. Third, the system operates with zero emissions, helping reduce the building's carbon footprint and environmental impact. From an economic perspective, the system is highly durable with a service life exceeding 30 years and requires lower investment compared to active solar thermal system. Overall, the Trombe wall provides a sustainable and energy-efficient heating solution. Although the system has many advantages, there are still some limitations. The performance decreases during cloudy or rainy days because the system depends on solar radiation. There is also a possibility of condensations forming inside the air gap, which may affect efficiency. In hot climates, overheating can occur if proper ventilation is not maintained. Additionally, the system requires proper south-facing orientation for maximum solar gain, and the initial installation cost can be relatively high. For future improvements, several enhancements can be introduced. For example, adding phase change materials or PCMs for better heat storage, using smart automatic vent dampers, improving glazing efficiency, and developing better moisture control system. These improvements can further increase system efficiency and reliability. To conclude, passive solar designs play an important role in sustainable engineering and energy conservation. Our Trombe wall system successfully demonstrates how solar energy can be used for indoor heating without relying on electricity or fossil fuels. The design achieved an 8.72-hour time lag, a heat flux of 198 watts per square meter, and a significant reduction in heating demand. The system is environmentally friendly, cost-effective in the long term, and suitable for sustainable building applications. Finally, this project highlights the importance of integrating renewable energy concepts into engineering solutions for a greener future. Thank you very much.